Hello and welcome back to Chapter 10. Today we're going to look at Section 10.7, which deals with polar coordinates. So far, we've been graphing equations as a collection of points, and specifically those points are like XY coordinate points. Okay, and these are points that we've been graphing on what we call a rectangular coordinate system. Now in 10.7, we're not going to be dealing with a rectangular coordinate system, but rather a polar coordinate system. And before we get into what the polar system looks like, we need to kind of identify a few things first. So the first thing we're going to look at is we have a fixed point, and we're going to call this O, okay, and it essentially is the origin, but when we're dealing with polar coordinates, it's called the pole. Now when we take an initial ray from the pole, this is called our polar axis. Okay, and I have a diagram and I'll show you what all of this looks like here in just 1 second. From the polar axis, we have several points, okay, and each of these points is assigned what we call a polar coordinate. Just like with the rectangular coordinate system, we had an XY coordinate point. Well, here, since we're dealing with a polar coordinate system, our polar coordinate point is given by the value r and the value theta. And that's comprised of the points r, which is the directed distance from O to P, and theta, which is the directed angle. And CCW is counterclockwise from the polar axis to the segment OP. So now with our diagram, if we look at this point here, O, this is actually our origin or our pole. And it says that if we were to construct an initial ray from O right here, this is called our polar axis. Okay, and if I take and draw a line from O to some point P, this is how I'm going to find R. So R is the distance from O to the point P, and the coordinates for P is R theta. And just like when we were back in chapters 5 and 6, okay, theta is measured off from that polar axis. The actual graph of a polar coordinate system is also different than the current rectangular system that we've been using so far. And I'll show you that here in the next example. So right away, before we even read what the example says, if you notice, this right here is our graph paper essentially for the polar coordinate system, and it does look significantly different. We do have our 4 quadrants, however, we have all of these circles, okay, and they have different diameters or different radiuses. Then we have these angled lines here, and these are representing the radian or degree measure of the angle. So if I look at this here, this is really my pi over 6 line. This is my pi over 4, pi over 3, pi over 3 here, pi over 4, pi over 6, and so on. So now, when I go to look at it, the example, it says plot the given point in the polar coordinate system. And we're going to look at this point here first, 3, negative pi over 3. Now to graph this, I'm going to use the circles for my radius. And I see that this circle right here lies on the radius of 3. So then I have to plot the point negative pi over 3. Well, if you remember when we're graphing angles, angles typically go in a counterclockwise direction. Well, if I have a negative angle or radian measure, I'm going to go in the clockwise direction. So because it says negative pi over 3, I'm really going to go in the clockwise direction. So to plot this point, I want to go out to the circle that has a radius of 3, and I'm going to go in the negative pi over 3 direction. So I'm going to come all the way down here, and this is my point. And the only thing I have left to do is to draw the segment that connects from the pole through that point in this direction. And again, I have a radius that's equal to 3, and a theta value that is equal to a negative pi over 3. And now we're going to do the same thing for the next piece, which says that I have a radius of 2 and a theta value of pi over 6. Well, my radius of 2 falls on this circle right here, and pi over 6 is going to be this point right here. So I'm going to connect that point from the pole and extend beyond, and my graph is now complete. Now, one thing I want you to make a note of is when we were dealing with rectangular coordinate systems, each point had a very unique representation. In other words, there's only one coordinate point that had 1, 1. There's only one coordinate point that had the location of 2, -3, and so on. However, when we're dealing with polar coordinates, this is not the case. Okay? In other words, I can represent the polar coordinate point r theta as r, and then take theta and add or subtract any increment of 2 pi. And if you remember, 2 pi is really 360 degrees. So I can either go in the positive direction or the negative direction for an angle and still end up at the same place as long as I'm adding an increment of 2 pi. Now the other thing I can do is I can actually take that same coordinate point r theta, and if I take the opposite sign of r, I can then go and take my radian measure or my angle measure theta and add or subtract the quantity of 2n plus 1 times pi and still get the same angle measure. So example 2 is actually going to demonstrate that. Example 2 says to plot the point 2 and 3 pi over 4, and then we want to find 3 more polar representations of this point between a -2 pi and a positive 2 pi. I do apologize that I forgot to put the graph paper on here. However, here's the sketch, and I think we can make do. So to plot the point 2, 3 pi over 4, the first thing I'm going to do is I'm going to go out to the second circle, which happens to be this circle right here, and we're going to assume that these are increments of 1. So maybe I'll label these 1, 2, and 3. And then I have to find 3 pi over 4. Well, if you recall, 3 pi over 4 is actually in the second quadrant and about halfway through. So this point here is the point 3 pi over 4, and it has a radius of 2. Now for the second part of the problem, we want to find 3 more points in polar representation that really equals the same point to 3 pi over 4. So to do that, we're also given the restriction before we do that these points have to lie in between a -2 pi and a positive 2 pi. So if you recall, we were given the equation that said we could do r and then go theta plus or minus 2 pi n, or we could do the opposite of r and then theta plus or minus the quantity of 2n plus 1 times pi. And when we look at this piece right here, the 2n plus 1, if you think about what this really means, this is going to give us an odd number of pi. So in other words, I'm adding some amount of pi, whether it be 1 pi or 2 pi or 3 pi, but I'm adding an increment of pi to my original point. So if I am sitting right here at our point that we just found and I add an n is equal to 1, I'm really going to be adding an increment of pi to it because I'm going to go 1 pi, 2 pi, 3 pi, which is going to put me down in this quadrant. If I replace that with n with a 2, then I have 5 pi. So if I start at this point, then I'm going to go 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So essentially we're adding or subtracting some increment of pi. Now, with that being said, to find 3 more points, I'm going to start out with a positive, and I'm going to look at this case right here. So I'm going to keep my r value positive, which in this case is positive 2, and I can either add or subtract 2 pi n. Well, if I add 2 pi to 3 pi over 4, this is going to take me outside of the 2 pi range. So I can't add 2 pi, but I can subtract 2 pi. if I go 3 pi over 4 minus 2 pi over, or just 2 pi, this is going to give us a negative 5 pi over 4. So this right here would be 1 point. Now another point then, and I'm going to use this second equation, would be to take the negative value of r, which in this case would be a negative 2, and I'm going to add or subtract an increment of pi. So if I add pi to the already given 3 pi over 4, 3 pi over 4 plus pi will give us 7 pi over 4. So really, if I plot that, that's this point right here. And then for my third point, and I'll just write this next to that one, I'm still going to have the opposite of my r value, which is negative 2, and now I'm going to subtract pi from 3 pi over 4. So 3 pi over 4 minus pi is going to give us a negative pi over 4. And if we plot that, and I'm at a radius of 2, a negative pi over 4 is going to occur right here. Now, with polar coordinates, we actually have what we call a coordinate conversion. And to look at that, let's go ahead and look at the relationship between the polar coordinate and the rectangular coordinate system. Okay? If I have a line segment right here, and it's coming off from my x-axis or my polar axis, it's going to have an angle of theta. The radius will be right here, or this distance. And if I have a polar coordinate, then this is going to be given by r theta for this point here. Or in a rectangular system, this is going to be my point xy. Now, because the coordinate point xy lies on a circle of radius r, we know that r squared is equal to x squared plus y squared, which is the equation of a circle centered at the origin, just as we have right here. Now, if you think back to the chapters where we talked about trig, we have some relationships that deal with x's and y's and thetas. And those relationships had to deal with the fact that tan theta was really equal to y divided by x. We knew that cosine theta was equal to x divided by the radius r, and we know that sine theta is really equal to y divided by the radius r as well. So if I were to go and simplify and solve for my x and my y values, this here is actually going to produce the equation y equals r times the sine of theta. This equation here will produce x is equal to r times the cosine of theta. And now we can convert from polar to rectangular with our x and y values. Example 3 says to convert to rectangular coordinates. Now we're given the polar coordinate because I have an r value and a theta value, and I need to convert these to rectangular or an x and y coordinate point. So the first thing I'm going to do is I'm going to look at the fact that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And don't forget, if you're using your calculator, you have to keep everything in radian mode unless it tells you otherwise. So here, if I want to solve for x, my r value is 4, and I'm going to go multiply that by the cosine of 3 pi divided by 6. Okay, and this is really x is equal to 4 times the cosine. 3 pi over 6 really reduces down to pi over 2. And if you guys remember, when we look at our unit circle, pi over 2 occurs right here at essentially what is 90 degrees. And when I look at the cosine value at 90 degrees or pi over 2, I get 0, so 4 times 0 is really equal to 0. Now I'm going to do the same thing with y. Y is equal to r, which is 4, times the sine, and we already know that that's going to reduce down to pi over 2. And the value of sine of pi over 2 is really equal to 1, so we end up with 4 times 1, which is 4. So the actual coordinate point that I'm going to get from this then would be 0, 4. And this here would be the final answer. Now for part B, we have a similar process. And we're just going to use these equations given right here. So for my x coordinate, I'm going to now plug in a 2 for r, and I'm going to take the cosine of pi over 6. And the cosine of pi over 6, if you remember, is really equal to the square root of 3 over 2. So I have 2 times the square root of 3 over 2. My 2's are going to cancel, and that's going to leave me with just the square root of 3. Likewise, for the y values, we have r, which is 2, times the sine of pi over 6. The sine of pi over 6 is really equal to 1/2, so 2 times 1/2 equals 1, and my coordinate point then is going to be the square root of 3 and 1. Example 4 says to convert to polar coordinates. So I'm given a rectangular coordinate point and I want to convert it over to polar. Well, the only equation that you have that will convert or that deals with x's and y's and thetas is the equation tan theta is equal to y divided by x. So I can plug in what I know, and I know that tan of theta is equal to 2 divided by 2, which is equal to 1. So tan theta equals 1, and you're going to do this using your inverse trig function. And I know that when both x and y are positive, that occurs in quadrant 1. So I know that theta is equal to pi over 4. Now I'm going to have to go through and find my r value, and r I'm going to find by using r squared is equal to x squared plus y squared, or in our case, 2 squared plus 2 squared, which is 4 plus 4, or 8. So this is r squared. To find r, I'm going to take the square root of 8, which is really equal to 2 square roots of 2. So my coordinate point then is going to be r, which is 2 square roots of 2, and theta, which is pi over 4. Now for part B, B says that we have the rectangular coordinate point of -1, 0, and we need to convert this then to an angle first, and then I'll find my r value. So to convert to the angle, we have tan theta is equal to y, which is 0, divided by x, which is a -1. And this does give me 0. So tan theta, if you think back to your unit circle, gives you 0 at either 0 or pi. Now when I have an x value equal to -1, I know that it has to occur here. So then I know that theta is equal to pi. For our r value, we're going to use that r squared is equal to x squared, which in this case is 0 squared, plus y squared, which is a -1 squared. So r squared is equal to 0 plus 1, which is 1, and r is equal to 1 then. So our polar coordinate point then would be r, which is 1, and theta, which is equal to pi. Now, with polar coordinates, we can also do polar equations and rectangular equations. To do an equation conversion, to convert from a rectangular equation to a polar equation, it's actually not that bad because all we have to do is replace our x values with our cosine theta and our y values with our sine theta. However, to go from polar to rectangular, a little bit more work is required. So let's do a few examples with this. Example 5 says to describe the graph of each polar equation and find the corresponding rectangular equation. So for part A, I'm given that r is equal to 1. Now, in a polar coordinate, remember that if I have a radius of 1 or an r value of 1, that this is really a circle. And because I'm not given a theta, it's the entire circle. So I know that I have a circle with radius 1. Therefore, I can just say that x squared plus y squared equals 1. And that's all I have to do for part A. Now for part B, I'm given that theta is equal to pi over 4. So to convert this into a rectangular equation, I'm going to have to use the fact that tan theta is equal to y divided by x. So I can go tan, and I know that theta is really equal to pi divided by 4, and the tangent of pi over 4 is equal to 1. Well, I know that 1 has to equal y divided by x. So if that's the case, I can rewrite this and get y by itself and say that y is equal to x. So this graph would be a linear line in the form of y equals x. For part C, r is equal to the cosecant of theta. And if you recall, that means that r is really equal to 1 divided by the sine of theta. And if I get rid of my denominator, I can rewrite this as r sine theta equals 1. And I know that r sine theta is really equal to y. So now I can say that y equals 1. And I have a rectangular equation, and the graph then would be a horizontal line going through the point y1 or y equals 1. And last but not least, for r equals secant theta, I'm going to take a similar approach and say that secant is really equal to 1 over cosine theta. And again, I'm going to get the denominator cleared. So to do that, I end up with r times the cosine of theta equals 1. This here really is equal to x, so I can replace that with x and say x equals 1. And this graph would look like a vertical line through x equals 1. Now, for your pre-calculus fun fact, you are going to have to check either Weebly or YouTube for your fun fact tonight. Have a good day, and we'll see you guys tomorrow.